Hello everyone. In this video, we're going to be solving a very nice system of differential equations. Remember, I had told you earlier that I was going to try to bring an equation or a system every week, and it's probably going to be on Mondays. From now on in, I'll try to make it as much as possible harder as we go, okay? So we have the system, dx over dt, which is the derivative of x with respect to t, equals x squared minus y squared, and dy over dt is 2xy. And we're going to be solving this system in one way, but is there another way to solve it? We'll also discuss that. Okay, so this is a system of equations. X and y are both functions of t, and our goal is to solve for x and y, separately, of course, right? X and y can be related, but our goal is to associate x and t, and then y and t. In some cases, we do find that we find the relationship between x and y independent of t, and it's not always a good thing. That's also something we can talk about if time allows. So let's go ahead and take a look at this from a very different angle. I just want to say that this is actually a complex Riccati. Did I say that right? I don't know how to pronounce it. I'm guessing it's probably Riccati or something like that. But this is kind of like a special type of equation. And here's what we're going to use. We're going to go ahead and use z equals x plus iy. Of course, you can also write it as x plus yi, and I have a channel dedicated to complex numbers. If you're into complex numbers, even if you're not into, maybe you will end up being, it's called a plus bi. Go ahead and check it out. It'll give you a good foundation in complex numbers. So we're going to use complex numbers, but I want to write it this way. Z equals x plus iy. Y is the imaginary part. X is the real part of our complex number. So what happens when we introduce a new variable like this, right? Obviously, z is a function of x and y. And x and y are both functions of t, so z is also a function of t, right? Indirectly. So we can differentiate both sides with respect to t. But instead of writing dz over dt, dx over dt, by the way, dz might make you dizzy. So we're going to use a shortcut and use the prime notation. So when we differentiate both sides, notice that z, x, y are variables and I is a constant, which is the square root of -1, by the way, in case you didn't know. But it's going to look like this. Z prime equals x prime plus I times y prime. Because we're going to use the constant rule. And if you're adding two functions, you can separately differentiate them, right? But here's the critical part. We know that this is x prime and this is y prime. So now we can go ahead and replace x prime with x squared minus y squared. Yeah? And y prime with 2xy. Great. And this gives you what? If you are familiar with complex numbers, this gives you x minus y quantity squared? No. Because I is the square root of -1, this actually gives you x plus iy quantity squared. And let me explain what that means. Think about a plus b quantity squared. You square the first term, you square the second term. When you square it, you get something like I squared y squared, but I squared is -1, so this becomes x squared minus y squared. That's where you get that. And the rest is easy, pretty straightforward. So by using this type of substitution, we basically get something like this. Z prime equals this. But wait a minute, isn't this the same as z? Yes, it is. So we get even a better equation. Z prime equals z squared. Notice how from a system of equations, we go to a simple linear differential equation, which is actually fairly easy to solve because this is separable. Let's go ahead and to see how it's separable. Let's go ahead and replace z prime with dz over dt and set it equal to z squared. Now we're going to go ahead and separate the variables. And then guess what the next step is? Integrate both sides, right? Respectively. And when you integrate the left-hand side, you got to remember this. The derivative of 1 over z is -1 over z squared. So if you integrate 1 over z squared, what do you get? You get -1 over z. Good, great. So it's good to know. What about dt? That's going to give you t. Do not forget the constant, right? Great. So we can actually solve for z First of all, you can multiply both sides by -1. So it's going to give you something like this. But guess what? Since z is a constant, you can actually kind of absorb it. And let's say you call C1. This becomes -C1, but I'm going to call that C. Does that make sense? And then by reciprocating or flipping it upside down, you get something like -1 over t minus c. By the way, if you left it that way, that would be okay too. So no big deal, okay? Great. So we found z in terms of t. Isn't that great? Yes, but what is c? C is a constant, but you got to remember, we are in the complex world. What is that supposed to mean? It means that our constant number is not a real number, it is a complex number. So c we need to replace with a plus ib. Sorry, a plus bi, no offense, but this is SyberMath, so it should be okay. We replace c with a plus ib, and when you do that, you're going to get something like this. Z equals -1 over t minus. By the way, let's go ahead and fix this. I'm just going to use a c here because I don't like the minus sign. So this is going to become -t minus c. And then when I put the minus sign on top, it's going to be fixed. So I want to leave it that way for some reason. Okay? So this is our z, but I want to replace c with a plus ib. And guess what this becomes? This becomes a complex number in the denominator. So what are we supposed to do? Multiply by the complex conjugate. So this is like x plus iy, but I don't want to say x, maybe m plus in or ib. If you have something like mib, m plus ib, what do you multiply it by? You multiply by m minus ib. Does that make sense? That's the complex conjugate. So you have to multiply by t plus I minus ib over t plus I minus ib. You get the idea? That's the complex conjugate. Now, we're going to go ahead and simplify this. To simplify, we basically need to negate this. So it's going to be -t minus a plus ib divided by. Now, when you multiply these two things, you got to use difference of two squares, which turns into sum of two squares because I squared is -1. So it's going to look like this. T plus a quantity squared plus b squared. One thing to remember, a and b are real numbers. C is a complex number, which is appropriate, right? Because we work in the complex world. Remember, we are using z equals x plus iy. The constants are complex numbers, but a and b are real numbers. That's how a complex number is defined, okay? Okay, we found z, so what is the big deal, right? How do you find x and y? You got to remember this. Z is equal to x plus iy. So if we're able to split it into the real part and imaginary part, that's going to give you x and y. So it's kind of like two equations or two results in one, which is the beauty of complex numbers, obviously. That's why I have a separate channel that is dedicated to the world of complex numbers. Go ahead and check it out, okay? Now, I'm going to go ahead and split the real part and the imaginary part since the denominator is real after multiplying by conjugates. So it's going to look like this. This is going to be the real part. So we kind of split it. Plus I times b divided by the same thing. Okay, so the denominator is going to be the same. But what about the real part and the imaginary part? Well, this is the real part of z, which is x. And this is the imaginary part of z. Notice that the imaginary part does not contain I. It only has the coefficient of I. So x and y together, problem solved. Obviously, you can go ahead and write it in a nicer form like, okay, x of t is equal to -t minus a divided by t plus a quantity squared plus b squared, and y of t is equal to b over the same thing, right? Okay, fine. But what about a and b? Like, what are they, right? They're constants. They're real constants. So you can go ahead and replace a and b with anything. Basically, this is kind of like a family of solutions. Wait a minute. You solved for x and y in terms of t, so we're done. And you can replace a and b with any real number you want, okay? But is there another way to approach this problem? Yes, there is. So this problem can also be handled by some type of special substitution, but it's pretty interesting because you know what's going to happen when you do that? You're going to get an entirely, I don't want to say entirely different, but, you know, it's going to be very different. And I'd like you to kind of give it a try. how to solve it, but let me go ahead and give you some maybe pointers to help you in the right direction. So first of all, here's what we can do. We can go ahead and use polar coordinates, which is similar to complex numbers, right? So we can define, hey, suppose r squared is x squared plus y squared. Then you can kind of differentiate x squared plus y squared, which is going to give you 2x x prime plus 2y y prime. So here we differentiate with respect to t, but since x and y are functions, we use the chain rule, right? And then what we can do now is replace x prime with what it is. Remember, the original system gave us these, right? And then you get something like this. And then you can kind of expand it, simplify it, and at the end you're going to find something like 2x r squared by way of substitution. And then you can take r squared and differentiate it. And then you can use a ratio, y over x. So you can kind of set up, okay, suppose u equals y over x, and then differentiate it by using the quotient rule, and then you're going to get something hopefully helpful from there. But that's a lot of work, and guess what? That's going to give you a different answer, and I want you to find out why those two answers are very, very different. But this is our solution by using the method of complex numbers, and this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care. Don't forget to check out SyberMath and aplusbi. And until next time, bye-bye.